In this video, I am going to discuss how to draw SO2 Lewis structure, that is sulfur dioxide Lewis structure, and I will also discuss SO2 formal charge, hybridization, molecular geometry or shape, and I will also tell you is SO2 polar or non-polar, and I will also tell you whether SO2 follow octet rule or not, right? So first, we have to find out the valence electron of SO2. Actually, I will show you two ways to draw this Lewis structure of SO2. But you need to give time here, otherwise you will not learn. So, look, sulfur is an element of group 6A, that is why it has 6 valence electron, and oxygen is an element of group 6A, that is why it has also 6 valence electron. But here we have 2 oxygen atoms, so we have to multiply by 2. So 6 plus 12, that is totally we have 18 valence electron in SO2. So how many valence electron does SO2 have? The answer is 18, right? This 18 valence electron has two tasks at the same time. The first task is to connect these 3 atoms together. You know that sulfur is least electronegative than oxygen, so sulfur is the central atom, right? So let us connect these 3 atoms together. So to connect this sulfur to oxygen, so we need one bond or 2 dots, right, like this. So out of 18, here we have used 4. So how many electron left? 14, right? 14 valence electron left. So this 14 valence electron will be used to satisfy the octet of outer atom first. So the oxygen has 2, so it will maximum take more 6 to satisfy its octet. So now you have how many electrons? 8, right? So out of this 8, this oxygen also will take more 6 to satisfy its octet. So now you have just 2, so these 2 will come here, right? So now this oxygen has 8, this oxygen has 8, but this sulfur has 2, 4, 6, that this sulfur has only 6 valence electron, but to satisfy the octet rule we need 8. That is why, look, if I move this lone pair to here, then what will happen? Then this sulfur has 2, 4, 6, 8. This sulfur has 8 valence electron. This oxygen also has 8 valence electron, and this oxygen also has 8 valence electron. So every atoms satisfy the octet, right? So this is one of the Lewis structure, but to get the best and stable Lewis structure, you need to consider formal charge. That is, you have to draw such a structure where formal charge of all the atoms in the structure will be 0. So that is why we have to move electron symmetrically. That is, you have to move this lone pair here. You know that sulfur can break the octet rule, right? So here, for stable Lewis structure, sulfur has broke the octet rule. So look, here sulfur has how many electrons? 2, 6, right? 6, 8, 10. So sulfur has broken the octet rule. So, but every oxygen follows the octet rule, but sulfur doesn't follow the octet rule. So if I draw here, then I have to draw like this. So this or this is the stable Lewis structure, right? Okay, let me show the another way to draw this Lewis structure. So you have SO2, so you need to draw the Lewis structure. You know that it has 18 valence electron. So sulfur is the central atom and oxygen is the outer atom. So at first you have to find out the valence electron, then you have to decide how many lone pairs the central atom will get. So to do so, you have to think about the multiple of octet. Look, this sulfur will take 8 valence electron to fulfill its octet at first step. So here we have 18 valence electrons. So we'll consider the multiple of 8. So the multiple of 8 is 8, then 16, then just add 8, then 24, right? 24. So here we have 18. So this is the base, right? So look, 18 minus 16. So we have 2. So these two electron will be lone pair. So first place the lone pair here, right? And to that to get the base Lewis structure, you have to consider the zero formal charge for all the atom. But here consider for sulfur, we will put zero formal charge for sulfur. So what will happen? We will use this formula: formal charge equal to valence electron minus number of bond plus number of lone pair, right? So for sulfur, look, valence electron we have 6 minus number of bond we would like to find, then here lone pair 2. We will do the math. So we are targeting to put zero formal charge for sulfur. So formal charge we will consider 0. Now let's do math. 6 minus 2. So 4 minus, if you subtract, then 4 minus B. So if you take B here, then 4. That is number of bond this sulfur can form is 4, right? So let us do that, right? So we have 18, here we have used 2, 4, 6, 8, 10, right? So this oxygen must take here 4, right? So this oxygen has 4 valency electrons, so this will take more 4, this will take more 6, 4. Now count. If you count, then you will get 18 valence electron. 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is the best Lewis structure, right? Okay. Let me show you another formula for finding the formal charge of all the atoms. So formal charge equal to valence electron minus half of bonding electrons minus lone pair electrons. So for sulfur, the valence electron is 6 minus a half of bonding electrons. Here bonding electrons 2, 4, 6, 8 minus lone pair, here 2. So 6 minus 4 minus 2, that is 6 minus 6 equal to 0. The formal charge for this sulfur is 0. And consider for this oxygen, so its valence electron is 6 minus half, bonding electrons here 2 4 minus lone pair. Lone pair over oxygen is 4. So basically we are getting 6 minus 2 minus 4, right? 2 minus 4, that is 6 minus 6, that is 0. So the formal charge of oxygen is 0. This oxygen will have 0 formal charge. So this is the way to find out the formal charge after considering the bonding electrons and lone pair. So here is the another way, right? Okay. Now let me show you the another way to find out the formal charge so that you can be a master. Look, this is the easy way. So look, I'm going to find out the formal charge for this oxygen. You know that in a neutral atom of oxygen we have 6 valence electron, but here we have 4 valence electron, and we have to take the half 2 4, and here we will consider half, that is half of 4 is half of 4 is 2, so 2 4 6 0, right? So for sulfur, look, we have 6 valence electron in neutral sulfur, but here we have assigned 2 4 6 0, right? Okay, so now you know how to find out the formal charge of each atom in sulfur dioxide atoms. Now I am going to discuss about the hybridization of sulfur dioxide. Look, for hybridization, look, we have one electron region here, and here we have pi bond and sigma bond, pi bond, sigma bond, but for finding hybridization we don't consider pi bond. That is why we have for lone pair we have one electron region, and here we have one electron region, right? And here we have one. So 1 2 3, so the steric number of sulfur is 3. This means that you need one s orbital and 2 p orbital, that is sp2 hybridized. This sulfur is sp2 hybridized. This oxygen also has 3 regions, 1 2 3. So this oxygen is also sp2 hybridized. So since this is sp2 hybridized, the shape or electron geometry of this compound is trigonal planar, right? But due to presence of this lone pair, the structure will be bent structure, like V type structure, right? V type structure or bent structure, right? Bent structure. So electron geometry or according to hybridization, its geometry or shape is trigonal planar, but its molecular geometry or shape, when you are considering the repulsion of lone pair, is bent shape or V-type shape, right? Now I am going to answer, is SO2 polar or non-polar? Look, this oxygen is more electronegative than this sulfur. This oxygen is more electronegative than this sulfur. So this bond is polar, this bond is polar. Every polar bond will have a dipole moment. So this is the direction of dipole moment. This is the direction of a dipole moment. So this bond has dipole moment, this bond has dipole moment. Now you have to think about the net dipole moment of this compound. That is, you have to see whether these two dipole moment is cancel each other or not. Due to bend shape, these two dipole moment doesn't cancel each other. That is why this molecule will have net molecular dipole moment. Here the word is important, net molecular dipole moment, right? So net molecular dipole moment is not zero. That is why SO2 is a polar molecule. Okay, actually you know that this is a vector and this is a vector, right? It's this is y component and this is x component. If x component cancel each other, but this component y component doesn't cancel each other, right? So this molecule will have net molecular dipole moment, that is this is polar.